Добрый день, уважаемые коллеги, уважаемые участники семинара. Э, Прежде всего, я хотел бы поблагодарить руководителей семинара и особенно профессору Равшанака за приглашение и предоставление мне возможности выступить в таком научном семинаре. Можно на английском или как?
Пожалуйста,
Можно, да?
пожалуйста, никаких
Да,
проблем.
вот у меня просто слайды все на английском.
Да.
So the title of my presentation is called Inverse Source Problems of Pseudo-Parabolic Equations. And in this work, I will consider one inverse source problem for nonlinear pseudo-parabolic equation perturbed by P Laplace operator and adding some nonlinear terms. So first, I will discuss on pseudo-parabolic equations and some their modifications, and then I briefly consider some on direct problem and then on inverse problem. So the main objective of this work is the following equation in form 1. It is called pseudo-parabolic equation, where U is unknown function, and here coefficients kappa, beta, and the gamma are given numbers, positive. Namely, beta is strictly positive. It is the coefficient, diffusion coefficient, and the kappa here we consider in non-negative. It is sometimes called relaxation coefficient. And the gamma is also given number. It's finite number. It might be positive or negative. And the p and the sigma exponents of nonlinearity, also given numbers. In generally, we assume that they are greater than 1. And the function f is given. When p equal to 0, 2, and the gamma is 0, or sigma equal to 2, then equation 1 becomes classical pseudo-parabolic equation like 2, and it is also called Sobolev type equations. And there are many works on inverse and direct problems on these equations. According to the many works, published works like this, such type equations have various applications. For example, such type equations methods in mathematical modeling processes, physical processes such as diffusion process, electrological fluid flows, non-Newtonian fluids, for example, in particular, Kelvin void equation, thermodynamics, filtration, and so on. On physical justification, I may refer to the following works. And moreover, pseudo-parabolic equations, some works also use as approximation or regularization of parabolic equation by this term with small coefficient kappa. And why there is moreover, studying the parabolic and the pseudo-parabolic equations give us some preliminary information on some applied problems like Navier-Stokes equation or Navier-Stokes void equation, also called Kelvin void equation. It
Sorry,
means
what's
that
excuse me, please, what is the meaning of the pi in the Kelvin-Vogt equation? Gradient pi, number pi.
it is a pressure.
Pi is a pressure, yeah?
Pressure, yes. Usually
Yeah.
also denotes by P, just.
Yeah,
And
okay.
it means that if we obtain some results for parabolic and pseudo-parabolic equations, they might be also obtained for like these equations. If it is not possible to obtain for parabolic and pseudo-parabolic equations, it's too hard to say that it is also held like these equations.
So,
Why?
Kelvin-Vogt system, sorry, U, what is the meaning of U? Is a velocity or concentration, or what is it?
U is the velocity of fluids.
Velocity.
Yes.
In Kelvin-Vogt equation too, yeah?
Yes, this second equation is called Navier-Stokes void equation, also Kelvin void equation. Here, the difference is just adding this term. This is indicates the relaxation effects of fluid.
In case when kappa is 0, it's the same, yeah?
Yes. When kappa is 0, it becomes the Navier-Stokes equation modified.
Yeah, modified. It's
Yeah.
concerned with plastic, I think. Yeah.
Yes, yes. Why we generalize like this P Laplace operator or adding by like these terms? It is not just mathematical generalization or modification. It is also has physical meaning. For example, in the fluid dynamics, this exponent indicates the type of fluids. For example, if P between 1 and 2, then fluid is pseudoplastic. And the P when P equal to 2, it is Newtonian fluids.
It's
Newtonian.
Laplacian, yeah.
Yes. And when P greater than 2, it called dilatant fluids. So this is a modification by P Laplace operator indicates come from type of fluids like this. So this I think this term it is also called memory term. Damping term. It also has some meaning. For example, in case gamma is negative, then this term affects us absorption effects gives in the system. And when gamma is positive, then this term works as source term. Usually when gamma is positive with source case, then usually for parabolic and pseudo-parabolic case, effect happen blow up effects, or other words,
The solution tends to
non-existence global in
infinity.
time.
The solution tends to infinity.
Yes, energy function goes to infinity.
At the finite time.
Infinite time, yes, right.
Yeah.
And in case gamma is negative, then whole extinction effects, or also
like dispersion.
Yes, the energy.
Diffraction, I think so. It disappears. Yes, it's with time.
Yes,
No?
in this case, the energy function vanish at finite time after some vanish time, like this effects.
Yeah.
So modified Navier-Stokes equation is also considered in book Lyons, Galdier, and also with absorption term, also Antonsev and Oliveira in these papers. So this modification by P Laplace operator is important. So direct problem now for like
In the book of Lyons, there was a proof of the existence in generalized Sobolev spaces, I think, not classical.
Yes, existence and the uniqueness as possible.
But only in Sobolev classes, not classical.
Yes, on Sobolev classes.
Yeah.
Yes.
Thank you.
So direct problem. Direct problem consists finding u from this equation 1 under the initial and the boundary conditions. All this work we consider omega as bounded domain. Considering bounded domain is Rd, where d is the dimension of space and it is greater than 2. Boundary is smooth. The Qt denotes the cylinder. So pseudo-parabolic direct problems for pseudo-parabolic equations well solvable than parabolic problem. For instance, direct problem for Kelvin-Voigt equation, classical Kelvin-Voigt equation, has unique solution, global in time, even in three-dimensional case. While this in Navier-Stokes setting, it is open problem. So it is like this effects also true for pseudo-parabolic case. In direct problem setting, pseudo-parabolic is well solvable. But in inverse problem setting, it is opposite. So there are many works on direct problems for pseudo-parabolic equations, from classical equation to more generalizations. And on the direct problems, I may refer to the following works from classical to more generalizations, such type equations. For example, on direction of generalization on P Laplace operator with constant exponent or given function depending on space or time or both variable were studied by Antonsev and his co-authors in their works. For instance, their latest work is the first two paper, where they considered initial boundary ball problem for first equation with exponent given function p depending on space and the time variable. And they obtained under some assumptions on the data uniqueness and the existence of each solution. And when this Laplace operator modified by also P Laplace and K's with the exponent given function sigma pi and also this, it was considered in my work in 2023, and they obtained the blow-up results, global non-existence, and large time behavior solution of like this, asymptotic properties of solutions. So also there are also some works on pseudo-parabolic and parabolic equations which exponent depending on subsolution or some function of given function subsolution. So like these equations also have applications. For example, they use it like this processes denoting digital images. Another problem is, for example, in this paper, Antonsev and Rodriguez, they considered stationary thermoconvective flow of non-Newtonian fluids, describing by this system, where B is the velocity, theta is the temperature, and S is deformation rate tensor. If they are possible to find temperature from the second equation in this form, anyway, then substituting this, the first equation here, we obtain single equation, stationary equation, which exponent depends on subsolution V. So there are also like these problems, equations, which P Laplacian, which exponent depending on some functional depending on subsolution. So now we consider pseudo-parabolic equation with P Laplace operator, which exponent depends on U, like this. And this work is related on this parabolic problem. This parabolic problem, this problem were considered by Antonsev and Shumarov in 2020 in this paper. And here U, P is given function, like this, depending on LU, where LU defined by in this form, and the P minus P plus is upper and lower bounds, and it is in this interval, and the alpha exponent in this functional also between 1 and 2, and they are obtained the following result under some assumptions on the data with under ranges of in these ranges alpha and the P minus and the P plus, they obtained the unique existence of the weak solution. So here we consider the pseudo-parabolic case. It was recently published in this journal with Shumarov. And here PU considered in this form. P depends on LU, and where this functional LU defined in more general setting, where G, and G is given function satisfying like these conditions. In generally, we assume that P minus P plus greater than 1 and finite, and the function J satisfy like these conditions. And we consider this problem two parts. First, we consider when kappa, the coefficient in this term is strictly positive, and the second part is when kappa is non-negative case. So if G equal to this and gamma is 0, then we obtain the parabolic case. When kappa is 0, we obtain the parabolic problem, about parabolic problem. So here, this is a definition of weak solution about pseudo-parabolic problem.
Can you show again the problem 5.7? Yes.
This one, yes.
5.7. Yeah, you consider G, and the G is on the next slide. G is a continuous differentiable according to S, yeah?
Yes.
Alpha,
yes.
what, there is nothing about alpha. Alpha is any positive or?
Alpha is greater than 1 in this interval.
Greater than 1. Yeah,
yes.
greater than 1.
Yes.
Yeah, it means if it equals
generally, but in the theorem, we some restrictions there on alpha.
Yeah, but if and the derivative may grow, there S alpha minus 1. Yeah, and L alpha. Yeah. Okay, thank you. And
next, this is a definition of weak solution. It understood in the following sense: U and U in these spaces, and the initial condition holds Ohm's theory in omega, and for every test function like this, hold this identity 12. So this is the definition of weak solution which we work. So this is
no, please back again the definition. Okay. It's U depends on xt, yeah.
Yes.
And P of U depends on xt too. Yes. This condition phi depends only on
both variables x and t.
Both x and t. Yeah.
Yes.
And you transfer all the derivatives except one, yeah, to phi.
Yes. No, just the first derivative.
Yeah.
Time derivative U.
In those articles, it's called the strong generalized solution. Now you call it weak solution. Yeah.
Weak solution. Yes.
Yeah. Usually weak solution if there is no derivative of the function u. You can transfer all the derivatives to phi, but only the half, yeah?
Yes. But only it half. Depends. Some works, for example, in works of Ladezhinskaya, they usually this called weak solution. And they is called strong solution when all derivatives in equation has in L2. Usually called this strong solution.
But sometimes the weak solution
yes.
transfer all. But in this case, there is no uniqueness here. Okay, thank you. Yeah. Please.
So this is a case. First, we consider when kappa is strictly positive, the pseudo-parabolic case. Then under assumptions on the data, 13 and 15, and the exponents satisfy this condition 16. Then the problem 5 and 7 has unique weak solution U in this case. So next theorem, and the solution satisfy this estimate this estimate. And the next we consider this problem with when kappa is non-negative. Non-negative, it means that kappa also might be equal to 0. In this case, under above assumptions 10, 13, and 14, under the restrictions on the exponent p and the alpha like this, then the problem, above problem has unique weak solution. Moreover, when kappa goes to 0, then a solution of pseudo-parabolic equations converges to corresponding parabolic solution. So here we work as pseudo-parabolic problem works as regularization or approximation of parabolic problem about. And in this case, we extend some restrictions in the first paper, Antosov and Shimarov. For example, in the parabolic case, they prove it under this condition. For example, P minus, their lower bound. D is a dimension. And alpha also their restrictions between 1 and the 2. In the pseudo-parabolic case, there is no lower bound, just greater than 1. And moreover, upper bound also extended like this. For example, in two-dimensional case, any finite constant alpha is. And when d greater than 2, bounded by this. So the results also hold for when kappa equal to 0. It means that it's also for parabolic case. So like pseudo-parabolic equations also might be works as regularization or approximation of parabolic problem. So, but in both case, in parabolic or pseudo-parabolic case, exponent not directly depend on u, depends on some function of u. In general dependence of p of u, in evolutionary equations open. However, there are some stationary case, which stationary elliptic equation like this with p Laplace operator. And this problem was considered by Shipot and Oliveira in 2019. And they obtained under like this restrictions, the existence and the uniqueness results, where lower bound also D, when P depends on U. If here P depends of some function of U, like above, then there is no like this restrictions.
D is positive or not necessary?
This is a dimension of space.
Dimension.
Yes.
Okay.
D.
It must be greater than dimension.
Yes. But like these results for evolutionary equations open. So next we consider the inverse source problem for like this pseudo-parabolic equations. Namely, we focus on this problem. The inverse problem consists of finding u and the coefficient f of t, right-hand side, under the overdetermination condition in the form 22. So this is right-hand side is source term, and usually F is called intensity of external forces. So here we P and the sigma constants, given constants. The inverse problem consists of like this. So the function j, u0, omega, and e are given. In generally, we assume that the exponents greater than 1, and we also consider in two cases when gamma is positive or negative in two cases. And the studying of inverse problems, especially recovering right-hand side depending on time variable, depends on form of integral over determination condition, measurement, additional condition. For example, if we consider this problem instead of 22, use like this condition 24, like this condition also use it in this following papers: Antontsov, Aichanov, Ashurova, and Yaman also in 2012. Also, my works with Shakir Aidos, 22. And this is a particular case of above condition 22. For example, if omega has like this form, special form, then after integrating by parts, we obtain like this condition. Moreover, also consider it might be considered in this form 24. This is from mathematical point also is possible, because in pseudo-parabolic case, the main term time derivative from this term. So after integrating by parts, this is also reduces the form 24. But this type conditions from mathematical point works well, but in physical side, it is hard to justification of physical meaning like these conditions. But this condition 1222 is it is justificable from physical point, but in the pseudo-parabolic case, it causes some difficulties in mathematical setting. So there are many Works inverse problems of pseudo-parabolic equations. It starts from the 1980 paper Randall and Carlton, and there are also many works, various setting. So in order to formulate, before to formulate the weak formulation of inverse problem, first we multiply equation by omega. Omega is a function in integral over determination condition, and integrate over omega. After integrating by parts, we define f in this form by u. Here, f defined by gradient u, and also time derivative of gradient ut. So, and here we assume that this function e and the data satisfy also like this condition 27. So we define weak formulation of inverse problem as follows way. So definition of weak solution: the phi of function u and f is weak solution inverse problem 1922 if these functions in these classes in functional spaces and the u0 hold almost everywhere, and for every function phi hold this equality 28, where f defined by the formula 26. So this also can be formulated as a direct non-local problem by substituting f right-hand side. We also might be considered as direct problem, non-local direct problem. So for solvability of this problem, we assume that data of function, data of problem satisfy this following conditions: 29 and 33, like these conditions. Here we also consider this problem according to range of exponents. First, we consider in this case when both exponents p and sigma between 1 and 2, and here coefficient gamma is any finite number, might be positive or negative. In this case, we established the following result: global in time existence. Assume that above conditions 29 and 33 and this condition be fulfilled. Moreover, we assume that there exists a positive constant m less than 4. such that hold this condition 35. Then the inverse problem 1922 has a global weak solution in time, global in time weak solution. And there's a priori estimate 36 and 37 hold. So this condition, this restriction is appeared due to the form of integral overdetermination condition when we obtain a priori estimates for Galerkin approximation. I will show this later. So next we consider the case one of the exponents p and the sigma greater than 2. But in this case, we consider the problem in two cases according to sign of gamma. First, we consider gamma is negative, and one of the exponents p and the sigma greater than 2. In this case, we obtain local in time existence results. So assume that above conditions, this condition is be fulfilled, and hold in addition to 29 is the initial condition function. Here we generally just assume that in this space. And in this case, we addition to this hold in this space. Then there exists finite time T1 such that the inverse problem 1922 has at least a weak solution in this interval Qt1. And in this interval, in Qt1, hold above a priori estimates 36 and 37. Next, we consider the case when gamma is non-negative case, non-negative positive. And in this case, we also obtain local in time existence results. Assume that in addition to above the theorem 3, hold this condition 41, where S is maximum of 2 and the P, and the S star is the Sobel conjugate of S. And in addition to 29, hold this condition. In this
Sorry,
case,
what does it mean, the Sobolev conjugate of S?
Sobolev conjugate is Sobolev embedding inequality. We satisfy this. It is S is the 2S divided by n minus S.
The Sobolev conjugate, yeah.
Yes, it calls Sobolev conjugate.
2S divided by n minus S.
Yes, 2S divided n minus S.
Yeah, okay.
So this is the uniqueness, but there is uniqueness is the problem here. Just when P equal to 2, there is no P Laplace operator, and there is nonlinear terms, and with exponent sigma, and it satisfies this condition where 2 star is the Sobolev conjugate of 2. It is a 2 star. It is a 2D divided D minus 2. In this case, the all above solutions are unique. But in general setting, the uniqueness is unknown, open. I might say it like this. So this is the main results regarding to the above problems. Now we consider some particular cases which allows the global existence or omitting like this restriction like this. So if the J equal to omega, where J is right hand side, in this case equation 19 becomes in this form, where omega is the function in overdetermination condition. If we consider in this case, then all above results holds without this restriction, and some results might be also improved And the second particular case, if we consider, as I mentioned above, if we consider in this form, measurement in this form, we consider in this form, then all above theorems holds without like this restrictions, without like this restriction. And also hold their uniqueness results. But their right-hand side is more general case with J. But in this case, we also obtain the uniqueness results under the condition on exponents P and the sigma. And this was considered in this paper with Shaker Aitos, my PhD student, and published in 2023 in this journal. So next, we prove here proof of the existence results above on inverse problem. Here we use Galerkin method.
Sorry, can you show the formula number 33 again?
Statement of problem.
No, number 33. Formula, yeah. And before that, when you find the f of t as a function of solution, can you show this one next, maybe? Yeah.
This one.
Yeah, this one. There is some assumption about solution U, yeah, and then you put this ft to the equation, to the definition of the solution, like a weak solution. Okay, and f in this case is under the integral only.
Yes, non-local problem we obtain.
Yeah, and then the how to say, the smoothness of the solution which you find, it's enough to satisfy the first preliminary equation, the first equation. It's enough, yeah?
Yes, not first equation, in this sense.
Yeah, what? This is the main integral differential equation, this additional integral inside the right-hand side, yeah? Instead of f, you put these integrals.
Yes.
And then you have nonlinear integral differential equations, and you try to, now it is a direct problem, not inverse.
Yeah, non-local direct problem, yes.
Non-local direct problem. You find it, and after that you can, there is a theorem of uniqueness too, of solution of this equation.
Uniqueness, as I said, not in general case. And only when p equal to 0.
The uniqueness of the equation number 28, is it, it was proved or no?
You mean uniqueness or existence?
Uniqueness.
Uniqueness is in when p, no, there is no uniqueness.
Yeah.
Uniqueness only when p equal to 2. So without the p Laplace operator, there is no p.
Yeah. Now, I understand. Yeah. Okay, thank you. Sorry. About Galerkin method, yeah, please.
So we use Galerkin method, and this is the basis, Galerkin basis in this space. And we look the Galerkin approximation in this form, 44, where the coefficients Cgn defined from the following ordinary differential equations.
And how you can find the psi functions, psi1 and so on?
No, this is psi is the basis function. It is given function basis.
Does they satisfy some differential equation or not necessarily?
Yeah.
Which is I understand. Yeah. Thank you.
Yes. So after finding Cgn, we constructed the Galerkin approximations un, and then we pass to the limit when n goes to infinity. So convergence of Galerkin approximations to the solution of first inverse problem. In order to prove this, we obtain a priori estimates, uniform a priori estimates. So it is also considered according to the cases of range of exponents like this. First, we consider in this case, and in this case, we obtain like there's a priori estimate 49, where K1 independent of N, uniform estimate. So the main difficulty here is when we study the direct problem. In direct problem, first we obtain by multiplying equation by UN, we obtain the first a priori estimate. After obtaining the first a priori estimates, we obtain the second a priori estimates. It is for time derivatives, obtain derivatives. But here, in this case, due to this f in the right hand side, also appeared time derivative of gradient of time derivative. This is the main difficult. So in this case, we cannot obtain the first a priori estimate. We obtain together this. So first multiply the equation 45 ckn and the derivative of ckn and the sum up by k from 1n to n and add these results. Then we obtain like this equation 50. So their right hand side is like these terms, and we estimate all of these terms by using Sobolev embedding inequality, Gilder and the Young inequalities in the following form. First, we consider the case when P and the sigma between 1 and 2. So first we obtain estimate Fn like this in this form, and this term in this case I should note that if gamma is negative, then this term will appear in left hand side. No, there is no right hand side, this term. But in general, we consider in the right hand side. So obtain this like inequality, estimate G1, G2 using the here Gilder inequality, Young inequality, like this. Here there's terms G2 also like this, G3, G4 in this form, and plugging all this inequality into 15, we as results we obtain like this inequality 57 differential inequality. So here A, B, and the C1, C3 defined by in the following way, where epsilon E are arbitrary constants. Now we choose this arbitrary constants epsilon, but there is no arbitrary. For example, epsilon 4 also appeared in this here and there. So there is some restrictions on epsilon 4. Also, constants are arbitrary. So here we choose first choose epsilon 1, 3, 4 this in order to be A and B to be positive. So here for epsilon 4 there is restriction like this. There it should be bounded below and upper bounds. There k is any number greater than 1, and but here the maximum bound is 4 for this epsilon 4. So, like this condition is not trivial. For example, if we take like this, then we get that A and B are positive. So choosing like this way, we obtain inequality 59 in this form. Where A and B are positive. So here we use it also this inequality, embedding inequalities, when beta and the eta are less than 2 in this case. So for the inequality 59, using Granwall inequality, classical Granwall inequality, we obtain estimate 60 in this form. So plugging this, using this for this term 51, we obtain also integrating by time variable, obtain also for estimate for this. So this is a proof of lemma one in case when gamma is exponents between 1 and 2. And next we consider this case, one of these exponents greater than 2, and the gamma is positive case. In this case, we use this equality for energy equality above institute of here. Here this term was in the right hand side in this case. But when one of the exponents greater than 2, we use for this this equality. This equality. In this case, the energy equality has the following form, 61. So here G1 and G3 given above. So they estimated in the following way: Gilder and the Younger inequality, also Sobolev inequality in this form. Here we keep this norm, gradient P. In the first case, we use it by using Gilder inequality. We change this by L2 norm. So substituting this and choosing also again this epsilon constants with the suitable values, we obtain like this inequality in this form, 65, where y of t, this function, we integrate, and after this, we obtain like this inequality. In the right-hand side, where y is power mu. Mu is number like this greater than 1. So sigma here is minus is minimum of 2 and the p. 2 and the p. S is maximum 2 and the p. So we obtain this inequality in omitting this second integral term in the on the left-hand side, and using nonlinear Granwall inequality. For this inequality, we obtain estimate in this form, 67. We obtain this form, and here using Granwall lemma, nonlinear, we obtain estimate in this form. For this holds for t such that less than t1, which define it in this form, where C5, C6, and all defined by date of the problem. So the case gamma, when gamma is negative case, this case is more similar to this. In this case, this term is appeared in the left-hand side. There is no right-hand side. So it is more simple than this. And under this a priori estimates by reflexivity and some weak compactness, we obtain the following limits. UN converges in this, and the main difficulty is to prove this. Here this converges S, some function, and this is R. So we should prove that S is.
You can prove that it's weakly, yeah.
Without N. Yes.
But arithmetic mean values can converge strongly, yeah. By it's well known. Yeah. If you have arithmetic means, sum from 1 to n divided by n, it will it converges strongly, to Yeah. No, okay, it doesn't matter. But weekly is enough to prove the existence. Okay.
Here also use Lyon's open compactness lemmas.
Because there was a Banach-Sachs theorem, you know that Banach-Sachs theorem. It means that no, okay, for the proof to prove the existence, it's enough to consider the weakly convergence here.
Mhm.
Okay. And, it means that this Galerkin approximation converges weakly convergence to solution.
Yes,
Is it right? Yeah.
we in weak sense, yes, right.
There is assumption that omega must be not how to say near to constant. It's so or no? Omega. This is the
Omega,
yeah.
for omega, we assume that like this condition. This in this space.
Yeah, but there is no condition. But can you show the formula 61 maybe or 62?
Okay.
Yeah, next. Oh, stop. Where is the yeah? Next maybe next. And where is the A? Next. Yeah. Yeah. Stop.
Yes.
A must be possible. Must be positive. Okay.
Yeah, A should be must be positive. Yes.
Positive. In this case, right hand side must be less than 2.
Yes. Yes.
If G is arbitrary epsilon 2, you can do it only when the gradient omega is very small.
Yes. Yes.
It means that omega is almost the constant. There is no assumption, but there you can use it, yeah?
Yes. Yes.
Because A must be positive.
But there is not just gradient omega. Might be G also might be less than very small.
Yes, G. Yes, maybe if G is given, and omega is an additional condition. Yeah, additional for inverse problem.
Yes, also given function in additional condition. Yes.
If you try to find the solution to inverse problem, yeah, you need to consider the additional conditions. Additional condition is concerned with omega. Yeah, and if G is given, yeah, and epsilon, you see, if epsilon is small, this norm must be smaller. Yeah, yeah. Thank you. It's I understood. Yeah, thank you. Thank you. You may continue.
Yes, this is under using the compactness lemmas, open Lyon's lemma, we also obtain the strong convergence UN in this space. And by Ries-Fischer theorem, UN converges almost everywhere in Qt. So by using this Lyon's technique, we obtain that R is this. So this is proved. Now we prove the S is this term. Actually, this term. In order to prove this, we use monotonicity and Minty-Trek theorem results. So in order to prove this, first we uh, we assume that this is equal to this. This is hold 79. And using above all limits, we pass to the limit in the Galerkin equation. And as a result, we obtain for limit function 81, where S is assumed like this. But we prove later this. So here we use monotonicity inequality. We construct this form where this is positive by monotonicity inequality. So after substituting this above using this 80 and 81 for xn for this, we obtain like this inequality, xn it is positive and equal to this. Here we substituted the 80 and the 81. So after passing to the limit, we obtain like this inequality for any z, 84. So taking z in this form with arbitrary function c and the positive delta, we obtain like this inequality. From this passing to the limit by eta, we obtain and by arbitrary of the function sigma, we prove that S is actually this one. So in the case when gamma is negative, here in the when gamma is positive, we also use it like this convergence 78. The above this follows this 78 follows from like this assumption, like this assumption, sigma less than 2 star. But in the case gamma is negative case, there is no like this assumption. For example, where here there is no assumption like this. But in this case, when gamma is negative, we use the monotonicity inequality for in this form for both nonlinearity. Xn we take in this form. Also this and this term. So on a similar way, we passing to the limit, we proved this existence. So the uniqueness is standard. We assume that there is two different solutions, and for difference we obtain equation problem, and then obtain estimate for this. But due to the appearance on the right hand side, also time derivative, due to this like this, there is very difficult to prove the uniqueness. But without the P Laplacian case, it is possible to prove. So that is all I have finished. Thank you.
Okay, thank you very much. Any questions? Может быть, есть вопросы?
Can I ask a question, please?
Yes.
Can you open the formula 77?
This one?
Yes. Yeah. You see, here you proved that R is equal to this function very easily. That you have this almost every convergence, and then using this lemma from Lyon's book, you can get that R is equal to this. But why you cannot do the same with S? So
because there is no strong convergence gradient UN.
Oh.
Yes, here just
here, 76 you have for gradient also?
No, there is just for U.
Yes.
Yes, if there is results for gradient UN strong convergence, then it is possible to like this way. But there is no
well, you see, in 76 you don't have anything for gradient.
77?
Yeah, 77 also no gradient. Where is gradient?
No, there is no gradient. Just U.
Yes. Yes. But why you cannot do the same with S? Oh, you have here gradient. Ah,
Gradient,
I see.
yeah.
Oh, I see. Okay. Yes.
Нужны дополнительные производные.
Yes, in order to get...
То вот это S, он очень сложным образом доказывает, поэтому
Да.
там градиент есть, да, понятно.
Да.
Там обычная сходимость В2.
Когда это просто Лаплас оператор, можно тогда получить регулярности, вот, например, получить оценку на Лаплас.
Это когда P равняется двойке, нет?
Да, когда P равно двойку. Используя специальный базис, вот, спектральные задачи. А вот когда...
Базис вы берете как собственные функции некоторого оператора.
Да. Когда это Лаплас, просто Лаплас.
А берете собственные функции оператора Лапласа в качестве базиса метода Галенкина.
Да.
Понятно. Any questions? More questions? Еще вопросы, может быть, есть? Или какие-то замечания, может быть?
Вот еще один вопрос. Вот
Ага.
когда вы рассматриваете прямую проблему, задачу, когда
Мгм.
степень зависит P от U, да? P от
Да.
U. Да. Там, во-первых, никаких гладкостей от P не надо, только чтобы ограниченность, да, P.
Ну, P это почти это функция от P просто. Потому что
Да.
это LU это такой функционал.
У не входит в P, интеграл от U входит в P.
Да, да.
Да, да,
P,
да.
P зависит не от функции самой U, а от
От,
интеграла. А
от
интеграл
Да, да.
уже он сгладил.
да, функция от
Ага.
на самом деле.
Он же плохо, если U имеет какие-то скачки.
Ага.
И P от U еще хуже делает эти скачки.
Да,
Но U, даже если имеет скачки, и от U уже нормальная функция, в общем-то.
да.
То есть
А.
здесь в норме L1 должна быть гладкость. L от U непрерывно зависит от U в норме L1, наверное. Ну и, не знаю, G зависит. Здесь главное условие на G. Какая она
Да,
по
Ага.
S. А по S она приличная. У нее первые производные есть по S. Видите, G
да, вот
штрих.
такие,
Да.
это G должен быть это
Это, если я правильно понял,
измеримый и дифференцируемый по S.
если U плохо меняется, допустим, то G' более-менее ее сглаживает, в общем-то. И тогда уже интеграл уже будет и еще лучше. И
Да.
он входит. Но, возможно, я ошибаюсь. Но э,
А,
а-
а
от,
вот смотрите,
да.
да. Ага. Там есть ли какие-то физические процессы, которые вот описываются именно таким степенью ПУ?
Я понял, что только из физических процессов это и возникло.
Ну, конкретно для, например, псевдопараболических нету конкретно написано. Но для параболических таких есть. Вот, например, в этих работах написано, что такие задачи встречаются вот в разных приложениях. Например, denosing the digital image like this.
Окей, окей.
Это
Вот, например, один из примеров, вот, например, тоже там приведены вот такие, например. Вот если тепловой конвекции из уравнения теплопроводности, вот, если мы можем, например, определить температуру через каким-то функционалом V, то подставляя туда, и можно получить такое уравнение. Вот. Да.
Да, да.
там,
И мы
видимо,
сейчас сработаем вот уравнение Кельвина Фойхта вот, в нестационарном случае. Но здесь температура зависит от температуры и система уравнения температуры. Но это незаконченная работа.
тут наверняка есть связь со стохастическим уравнением, потому что здесь, когда вы снимаете шум, там вот случайная величина, в каком-то смысле этот шум, и от уровня шума зависит, насколько сильно вот эта функция S зависит. В этом смысле, может быть, степень, она зависит от уровня шума.
Да,
Да.
на самом деле вот это, если это вязкости жидкости, вязкости, а
Но
вязкость это зависит от температуры, вот, например.
это если уравнение Фокта, там да, тогда действительно это вязкость.
Вот, например,
Хотя
здесь, вот
у
это
него
градиент модуль, вот это типа как зависит от, ну, связано с вязкостью, вот это.
вообще-то удивительно, что это Фокт работал в позапрошлом веке, а это описывает движение полимеров. А полимеры, они появились позже него. И так получилось. Значит, он предугадал как-то, в общем-то. Э, Тут, насколько я помню, я когда пробовал этим заниматься, полимеры, когда он крепкий, хороший, он подчиняется обычному закону механики. Но когда
М,
он, вы его нагреете, он становится как жидкость. И для него уже другое уравнение, а материал тот же самый. Просто режим меняется его работы. И
м.
поэтому нужно было написать уравнение, которое и на жидкость годится, и на твердое тело. Насколько я понял, вот отсюда возникло это уравнение.
Может
Вот,
быть, да, может
да.
быть.
Нет, вопрос Равшан Раджавович понятный. То есть имеет ли смысл заниматься задачей, если она не имеет приложения? Ну, значит, она имеет приложение.
Ну
Так
да,
что,
да.
Ваше Уважаемое, имеет смысл заняться этой
Да, но
задачей.
иногда просто мы усложняем, чтобы вот там математически мы можем решить, давайте усложним. Степень зависит от там еще что-то.
Вы же закончите физический факультет, да, насколько я помню? Нет?
Нет, нет,
Не-не,
нет. Математика.
Вычислительная математика.
ВМК, ВМК я закончил.
ПМК.
А,
Видите ли,
Да.
вот физик как-то спрашивал у математика, зачем у вас произвольная размерность n? n равно 3. Мы все знаем, что пространство трехмерно. И никаких нам четырехмерных, пятимерных не надо. Это время, это искусственное четвертое. Пространство реально трехмерно. Потом он рассматривает 5 частиц, общая координата получается 15. И он начинает спрашивать математика, что ты там говорил про n-мерное пространство? Поэтому вы никогда не знаете, где это может пригодиться. Сразу не надо от этого отказываться. Да. Ну хорошо, вопросов больше нет.
Можно последний вопрос,
Да.
да, Шавкат Ардёнович?
Нет, почему
Вот вы
последний?
когда,
Можете задавать.
когда, когда строите вот это галеркинские суммы, у вас вот этот коэффициенты сожитые, есть? Сожитые еще n, да? Вот. Э, вот почему они существуют? Э, Вы же должны подставить в уравнение ваше, да, и потом
Да.
для s вы получите какие-то задачи. Вот эта задача почему имеет решение?
Ну, там мы не доказали, что, ну, опираем на общую теорию дифференциального уравнения. Вот задача Каши, например. Потому
Нет,
что
ну,
это все нелинейности с n, это экспоненциально, ой, как показательная функция, поэтому удовлетворяет вот, условия Липчица, можно показать, что.
вообще
Локальный,
там,
да?
Да,
Локальный.
локальный, да.
вообще, насколько я помню, в методе Галеркина такой вопрос не возникает. Вы берете уравнение в многомерном пространстве, Банаховом, и берете проекционные операторы на конечномерные. И вот это,
Да,
когда берете проекцию, то берете, получаете просто, берете оператор проекта, он сам рисует коэффициенты. По нему вы находите n плюс первое приближение. И опять то же самое. Вот чем хороший метод Галеркина, это же тот же метод Рица, если быть условия ортогональности. В методе Рица вообще там нет вопроса о существовании, просто проект вы берете ортогональный, и там рассматриваете конечномерные уравнения и увеличиваете размерность постепенно. А в методе Галеркина там это уже не это в Банаховом пространстве, там может не быть ортогональной проекции. Но вообще-то вопрос понятный, конечно, да. Что,
Можно я отвечу на этот вопрос?
пожалуйста.
Вот когда мы применяем метод Галеркина относительно с, получаем откровенное дифференциальное уравнение.
Да.
Есть
да.
лемма Вищика, есть известная теорема Вищика, если вот эта система откровенного дифференциального уравнения имеет единственное решение, то оно будет нелинейным даже, будет разрешимо. Это доказано Вищиком. Это теорему мы можем ссылаться на это. Это будет ответ, хорошо раздел вашего вопроса.
Да.
Но вообще-то, вот, насколько я помню, у Конторовича и Акилова там этот метод подробно... И нет, еще есть хорошая книга, я неправильно цитировал. Пустынник, по-моему, Забейко, Красносельский, они, по-моему, написали книгу о проекционных методах. И там подробно вот этот, в общем случае, рассмотрен метод Галеркина. Он и хорош тем, что там легко строятся эти последовательности, труднее доказывается разрешимость, условия нужно проверять много. Так, больше к докладчику нет
На
вопросов?
вопрос это на вот, физический смысл, я хочу сказать вот такое слово. Вот когда я вот в 2022 году работал в Институте гидродинамики вот, на стажировке с Станиславом Николаевичем Антосовым, я ему задал вот такой типа вопрос. Вот, можно это физически, так как он сказал мне так. Нам Кажех сказал, что сначала давайте решаем задачу по математической, потом найдем физический смысл. Поэтому здесь акцент на математический.
Вы знаете, он не первый, кто это сказал. Адамар за 100 лет до этого сказал следующее. Вот математики, которые потом ищут физическое приложение, напоминают мне художника, который рисует пейзаж, потом берет в руки эту картину и ходит, ищет, где бы такой пейзаж находится, похожий. Ходит вокруг своего города, ищет по полям, по лесам. Вот то, что он нарисовал, что-то похожее, есть или нет. Вот это он ищет приложение. Значит. Обычно же берется другой, обычно берется уже готовый пейзаж. Но я понял. Вы говорите, в институте гидродинамики. Это не тот институт, где Монин был директором когда-то, нет? Это в Москве, да?
Нет, я не работал, просто у нас
Стажировки вы там.
стажировку был там-то, да.
Ага. Там, я
По-моему,
помню,
директором там я не был.
насколько я помню, там впервые появилось дифференциальное уравнение дробного порядка, именно Лаплас в степени 1/3. Это было 70 лет назад, да, 70 лет назад, 56-й год, да. Да, ну ладно, мы что-то отвлеклись. Так, доклад был, мне кажется, очень интересным, познавательным. И вообще-то у меня такое чувство, что было бы хорошо, если здесь можно было наладить продолжение в виде какого-то сотрудничества, да. Если удастся, конечно, да. Математика очень индивидуальная наука, но я сейчас смотрю, по этим вопросам публикации появляются с большим числом авторов. Вот, значит, все-таки сотрудничество возможно.
Да, да, да.
Например, в теории функций я вообще не знаю работы, где было бы два автора. Ну, кроме, может быть, вот Харди и Литтенвуда. А так, в теории функций каждый работает в одиночке, а здесь в одиночестве. А здесь, я думаю, возможно. Ну, это как пожелание. И я не знаю, участники семинара согласятся с этим или нет.
Да, конечно. Не, мы в частности применяем вот эти идеи, которые у Khompyша вот, для решения обратной задачи по определению правой части, когда правая часть зависит и от части пространственных перемен. Там вот этот Галеркин метод, там и эти оценки мы используем.
Здесь только f от t, а вы берете, чтобы и x там был тоже, да?
Да, да, да. Ну, конечно, уравнение попроще, да. Не такое, как сильно. Ну, вот у нас вот это возник вопрос, вот с Экатой, вот это самое. Но вы так не доказываете там из общих соображений, там степенной, поэтому там... Ну, вы там попробовали доказать вот это самое.
Один знает, оказывается, как их находить.
Да, да, да.
Да, понятно.
Ну, хорошо, да.
Спасибо, Khonatbek, за очень интересный доклад.
Спасибо
Вот,
вам
я надеюсь,
еще
что мы
за
сможем
представить
еще
возможность
не,
выступить.
мы сможем еще не раз услышать ваши презентации. Да. Тогда от имени всех я поблагодарю докладчика. Большое спасибо. Ну и
Спасибо
всем
вам.
всего хорошего, всего доброго.
До свидания. До
До
свидания.
свидания. Да. Саламат Балида. Всего доброго.
Анатолий, до свидания.